So we defined W0P of omega as LP of omega. Then we define WMP of omega. So this is for all m greater or equal to 1 integer. Now we want to define WSP of omega for all S in R. So this is our aim. So this is what we are going to do now. So we are going to study dual spaces, fractional order spaces, and trace spaces. Trace spaces are the Sobolev spaces defined on the boundary. Okay, so this is our program for the moment. So we start with the negative integers. So we have the following definition. Let 1 less than or equal to p less than infinity. Let p dash denote the conjugate exponent of p. Let m be a positive integer. Let omega contained in Rn be an open set. Then the dual of the space WMP0 of omega will be denoted by W minus M P dash omega. If P equals 2, H minus M omega is the dual of HM omega. HM0 of omega, sorry. Okay, so this is the definition of the Sobolev spaces for the negative integers. Okay, so remark. Now HM0 of omega, real Hilbert space. So in principle, by the Riesz representation theorem, can be identified with its own dual. This is the Riesz representation theorem. Okay, but we do not do so. Except when m equals 0, that is L2 of omega star is identified with L2 of omega. So we have, when we have a tower of Hilbert spaces, we will have H2 0 of omega. This is included in H1 0 of omega. This is included in L2 of omega, which is equal to L2 of omega star, and then we will have H minus 1 of omega included in H minus 2 of omega, and so on. So the dual of H1 0 of omega will be H minus 1 of omega. Dual of H2 minus 2 of omega is this. Now why do we have these inclusions? Because in general, if we have V contained in H Hilbert spaces, continuous and dense inclusion, H identified with H star, then we have V is contained in H, which is equal to H star, which can be identified as the subspace of V star. So this is a standard thing in Hilbert space theory. So whenever you have a dense and continuous inclusion, then the dual will be included in the opposite direction. That is true. And since we identify the two duals, so we have this dual, so you have this inclusion. Now it is obvious why we do not want to simultaneously identify V with V star, because then all of them will become equal, which is absurd, and therefore we always keep them separate. So when you have a tower of Hilbert spaces, so you have one space which is called the pivot space, which is identified with its own dual, and all other duals are separated, and you have, because of the continuous and dense inclusions, you have the dense inclusions and continuous inclusions in the opposite direction. Okay, so now one more thing, the presence of P dash in the dual is clear, because we are dealing with LP spaces, and therefore the conjugate exponent will naturally appear in the dual space. So but why do we denote the dual of WMP 0 omega by W minus M P dash omega, and not the dual of WMP omega itself? So why don't we call the dual of this as minus MP omega? Instead we are calling the dual of WMP 0 of omega. Now there is a reason for this. The reason for this is, now if you have W M plus 1, so M is positive integer, then if you take W M plus 1 P of omega, U is this, then du by dxi belongs to WMP of omega. So we'd like this to continue. So we would like, if U is in LP of omega, which is W0P of omega, then du by dxi should belong to W minus 1P of omega. Okay, we want this to happen. Now this will happen only with the definition which we have given, as the following proposition will prove. So proposition, let omega contained in Rn be an open set and let 1 less than or equal to P less than infinity. Let capital F belong to the dual of W1P omega, respectively W1P0 of omega. Then there exists F0 Fn in LP of omega, LP dash of omega, P dash equals conjugate exponent of P, such that for all U in W1P omega, respectively W1P0 of omega, we have f of v equal to, for all v, f of v equals integral on omega f naught of v plus sigma I equals 1 to n integral of omega fi dv by dxi dx. Okay. So if we define norm v 1p omega to be equal to mod v 0p omega plus sigma I equals 1 to n mod dv by dxi 0 p omega, which is equivalent to the norm defined earlier. What is that? We took the pth powers and then took 1 by p. Okay. Then norm f equals max 0 less than or equal to I less than or equal to n of mod fi 0 p dash omega. If omega is bounded and f is in the dual of W1P0 of omega, we can take f naught equal to 0. So we can forget about f naught. Okay, so let us prove this proposition. So let E equal to LP of omega power n plus 1, and let T from W1P of omega or W1P0 of omega, does not matter whichever, to E the natural isometry. Namely, T of V is equal to V dV by dx1 dV by dxn. Okay. Now let G equals image of T contained in E. So this is a closed subspace because it's an isometry. T is an isometry. So closed subspace of Banach space is also Banach, and therefore by the open mapping theorem there exists an S from G to W1P omega or W1P0 of omega. Inverse of T. So this is the open mapping theorem. So now you define H in G mapping to f of SH. So this is a continuous linear functional and extends to E by Hahn-Banach. So we have a closed subspace on which we have continuous linear functional. So preserving the norm, so this will extend it to by the Hahn-Banach theorem. So let us call that phi from E to R, and then phi restricted to G is equal to f of f composed with S. So but E is what? LP power. So this implies there exists f naught Fn belong to L P prime omega such that if V naught V1 Vn belongs to E, then phi of V, because it's just Rees representation theorem, is f naught V on omega plus sigma I equals 1 to n integral on omega fi V. Okay. And if norm V E is equal to sigma I equals 0 to n mod Vi 0 p omega, we have norm phi equal to max 0 less than or equal to I less than or equal to n of mod fi 0 p dash omega. This is just the product, dual of a product is given this way. Okay. And of course norm phi will be equal to norm f by definition, because it's a Hahn-Banach extension and therefore it's an extension. Now for any v in W1p of omega or W1p0 of omega, whichever we are considering, we have v is nothing but s of tv. Therefore f of v is equal to phi of tv, because phi of tv is f of s of tv. S of tv is same as v and therefore is phi of tv, and therefore that is equal to integral over omega f naught v plus sigma I equals 1 to n integral omega fi dv by dx. Okay, so that proves one part of the theorem. If omega bounded and f in dual of W1p0 of omega, then by Poincare inequality, enough to consider the isometry T from W1p0 omega to LP of omega power n, not n plus 1 now, namely TV is equal to dV by dx1 dV by dx, because the norm here is given by just the LP norm of the derivatives, and therefore we can take f naught equal to 0. So this proves the proposition. So now what is the how does this justify our notation? So let us take phi in d omega. So if we took phi in d omega, by definition, so f of phi can be written as, this is integral f naught phi on omega plus sigma I equals 1 to n integral omega fi d phi by dxi, which is equal to f naught phi plus minus d phi by dxi. Let me. So f naught acting on phi minus sigma I equals 1 to n df by dx dfi by dxi acting on phi as distribution. So these are the distribution derivatives. Okay, and therefore, so you can write this, or okay, let us leave it like that. Okay, so then d omega is dense in W1p0 of omega, and therefore you can say we can identify f with the distribution f naught minus sigma I equals 1 to n dfi by dxi. Okay, and therefore whereas if you are in the dual of W1p omega, we cannot do this for f in the dual of W1p of omega, because if you have a dense subspace, then the definition of the functional is completely determined if you define it on the dense subspace, whereas if you are in this, then to the whole space there can be many possible extensions, and therefore you cannot identify it with that distribution derivative there. And therefore if you wanted, so that is why we say that the dual, so hence since W1p0 omega contains derivatives of LP prime omega, we call it W minus 1 P dash omega. So that is the reason which we are doing. Okay. So now, so that justifies it. Now let us take M bigger than N by P. Then W1P MP 0 omega is contained in C of omega bar. Okay, and you have Helder continuity is also there. Therefore, if x naught is in omega and phi is in d omega, we write delta of x naught of phi equals phi of x naught, the evaluation function, the Dirac distribution concentrated at S. And you have mod delta x naught equals mod phi of x naught plus, which is less than or equal to mod phi 0 infinity omega, and that is less than or equal to, by the Sobolev embedding theorem, this is norm phi MP omega. Okay, so this implies that delta x naught defines a continuous linear functional on W MP0 of omega if M is bigger than N over P. Therefore, this is for any P. Therefore, delta x naught belongs to W M minus 1 P dash omega for M large enough. Now you can define, so having defined the negative things, now we can define W SP of omega can be defined in a variety of ways. And this gives rise to various types of Sobolev spaces. They are sometimes called Bepo-Levy spaces and so on and so forth. But the good thing is, if omega is a C infinity set, a smooth open set, then all the definitions will agree. So that is the nice thing about it. But depending on the singularities of the boundary, you may get different spaces, different function. The spaces may not be identical, and so we can, the various ways of defining depending on your necessity, how to define it. Okay, so one way of defining it is the following. Let 1 less than or equal to P less than infinity, and you take 0 less than sigma less than 1. Then you define W sigma P of omega equals set of all U in LP of omega such that mod Ux minus Uy by mod x minus y sigma plus n by p belongs to LP of omega cross omega. So you define this as W sigma p, and with the obvious norm. Namely the LP norm of this function. Okay, so that is the obvious norm. So now if S equals M plus sigma, M in Z, M greater than or equal to 0, you define W MP SP of omega is equal to set of all U in W MP of omega such that d alpha U belongs to W sigma P of omega for all mod alpha equal to M. Okay, so then this is how you define the spaces. Now W SP 0 of omega is d omega closure in WSP of omega, and W minus s p dash omega will be the dual of WSP0 of omega. So if P equals 2, we say Hs of omega and Hs 0 of omega. This is one way of defining the Sobolev spaces for all the things. So if P equals 2, we can define and omega equals Rn. We can also define Hs of Rn via the Fourier transform. So for S positive, we define Hs of Rn equals set of all u in L2 of Rn such that 1 plus mod xi square to the s by 2 u cap xi belongs to L2 of Rn. And the associated norm u square s Rn is equal to integral over Rn 1 plus mod xi square to the s by 2 s mod u cap xi square d xi. So this, when s equals m, we have already seen this when it's an integer. So we just simply do it the same way for all s which is positive. So now we show that this works for negative indices as well. So theorem, s greater than 0 real number, then h minus s of Rn equals set of all u now in the tempered distributions of Rn, okay, such that 1 plus mod xi square to the s minus s by 2 u cap xi is in L2 of R. Because if it's tempered distribution, you can define u cap xi and then we require that this is also true. So proof, we will do it only in the case s equals 1. Okay, so u in h minus 1 of Rn. Okay, then we saw there exists f naught fn in L2 of Rn. This we saw in the previous proposition, such that u equals f naught plus sigma I equals 1 to n dfi by dxi. We saw that this was the thing. So implies u belongs to s dash of Rn. Why is it so? Because L2 functions are in the tempered distribution. Derivative of a tempered distribution is again a tempered distribution, and therefore you have that u is in s dash of Rn, and therefore you have u cap. We have seen this is equal to f0 cap plus you have sigma I equals 1 to n 2 pi I xi I fi hat. So you have to multiply by this monomial. So from this it is clear that 1 plus mod xi square to the minus 1 mod u cap xi minus half, sorry, is in L2 of R. Because if I divide by 1 plus mod z square, this will be less than 1, and then fi naught are all square integrable, and therefore this will be integrable. Okay, therefore you have that. So this proves one way, namely if it's in h minus 1, then all these things are true. And now we want to prove the converse. Okay, so let u belong to S dash of Rn, and 1 plus mod xi square minus half u cap xi belongs to L2 of R. So let phi belong to D of Rn. Then the Fourier inversion formula, this is of course contained in S of Rn, and therefore by the Fourier inversion formula there exists a psi in S of Rn such that phi equals psi hat. This is Fourier inversion. Okay, so now you take k of xi equals 1 plus mod xi square power half, and k sub minus 1 xi as 1 plus mod xi square to the minus half. Okay, now u of phi equals u of psi hat, and since this is a tempered distribution, this is by definition u hat of psi. Okay, now k minus 1 u belongs to L2 of Rn, and k times psi belongs to S of Rn, because that's the definition of S of Rn. You have when you multiply by any such polynomial, you will have that it's in k of Si is in L2 of Rn. Okay. Okay. So because you have 1 plus mod xi square to the into psi square, and this is in S of Rn, and therefore this is also in S of Rn, and therefore this belongs to L2 of Rn. Okay, so therefore you can write u of phi equal to integral over Rn k minus 1 xi u cap xi k xi psi hat psi of xi d psi. So by the Cauchy-Schwarz inequality, you have mod u phi is less than or equal to k minus 1 u cap in L2, so 0 Rn into mod k times psi in 0 Rn. Okay, this is some constant which we don't have to worry about. So let us look at what happens to k psi. So k psi square 0 Rn L2 norm is equal to integral on Rn 1 plus mod xi square into mod psi square d xi. Now if I change the variable xi to minus xi, this will be integral over Rn. I will again get 1 plus mod xi square into mod psi of minus xi square d psi, which is equal to integral over Rn 1 plus mod xi square into mod psi hat hat xi square d psi, because by the Fourier, again by Fourier inversion, f double hat xi is nothing but f of minus xi. So you can check that very easily just by writing out the formulae. Okay, so this is equal to this, and that is equal to integral over Rn 1 plus mod xi square into mod phi hat xi square d psi, and that is nothing but norm phi in 1 Rn. So this implies that U defines a continuous, so you have this one is a constant and this one is less than or equal to a constant times is nothing but norm phi square, norm phi in 1 of Rn, and therefore U defines a continuous linear functional on H1 of Rn implies U belongs to H minus 1 of Rn. So we have proved the completely, and norm U square in minus 1 Rn is in fact equal to integral 1 plus mod psi square to the minus 1 mod U cap psi square d psi over R. Okay, and this. So now we can recover, for instance, we said that if m is sufficiently large, then you have delta is in W minus MP and so on. Okay, so if you have delta hat equal to 1, and therefore you have 1 plus mod xi square to the minus s by 2 is in L2 of Rn if s is bigger than n over. So this implies that delta belongs to W minus H minus S Rn if S is bigger than n over 2. So whenever you have the same thing we already proved, m is bigger than n by p, we said delta is in W minus MP, and therefore the same way, the same result we are recovering in the case p equals 2. Okay, so we will continue with this later.